So-called hydrated solids contain water molecules embedded within their crystalline structures. The example here shown represents a crystal of copper-2 sulfate pentahydrate. If we zoom in, we can see the embedded water molecules seen more clearly. If we look at 1 unit of copper-2 sulfate pentahydrate shown here, we'd see that for every 1 unit of copper-2 sulfate, it is surrounded by 5 water molecules. Despite having water in its structure, hydrated solids usually feel and look completely dry. Other examples of hydrates are shown here. What's important to notice is that in most hydrated solids, there's a fixed whole number ratio of water to the compound. In the case of magnesium sulfate heptahydrate, the mole ratio is 1 to 7. The other mole ratios are shown. The embedded water, or waters of hydration, can be removed by heating. The reaction shown illustrates that heating magnesium sulfate heptahydrate will yield an anhydrous or dry form of magnesium sulfate and 7 water molecules. We can calculate the percentage of water by mass in a hydrate from a formula. The calculation involves dividing the total mass of the water molecules in the formula by the formula mass of the hydrate. The calculation for magnesium sulfate heptahydrate is shown. This calculation shows that magnesium sulfate heptahydrate is about 51% by mass. Applying the same formula to copper sulfate pentahydrate, we see that it is about 36% water by mass. We can also determine the percentage of water in a hydrate from an experiment. To do this, what we'd need to do is to measure the mass of a clean, dry evaporating dish. And then we'd measure a certain mass of the hydrated solid into the evaporating dish. Using a hot plate or ring stand Bunsen burner, we then heat the hydrated solid until the water is driven off. What's left is your anhydrous solid. We can determine the mass of the anhydrous solid by massing it, of course, and determining the mass of the water liberated simply involves taking the difference between the hydrated solid and the anhydrous solid. So shown on the screen is an example of some of the data that we may collect from an experiment. A sample of Epsom salt has a mass of 8.723 grams. The sample is heated to a constant mass of 4.374 grams. This is the anhydrous form. And from this we can calculate the mass of water in the Epsom salt. What we do is we take the mass of the hydrated solid and we subtract from this the mass of the anhydrous solid. The difference between these two masses would represent the mass of the water, in this case 4.349. Then we take this mass that's liberated from the hydrate and we divide it by the total mass of the hydrate, in this case 4.349 divided by 8.723. And from this we get a percentage of water of about 49.86%. Using the formula as we did before, we see that water in magnesium sulfate heptahydrate should be around 51%. And so we would, in this case, have some experimental percent error. We can calculate that by taking the measured value and subtracting from that the accepted value and dividing that by the accepted value, multiplying by 100. In this case, we'd get a percent error of about 2.56%. What's also important to notice is that if we use the mass of the anhydrous solid and the mass of the water that's driven off, we can calculate the mole ratio of magnesium sulfate to water. And if we divide the mole values that we calculate by the lowest mole value, we arrive at a ratio that's almost a whole number ratio, in this case 1 to 6.64, but this is experimental data. We understand that ratio should be closer to about 1 to 7. So notice now the mass is 56.69. Notice that the appearance of the crystals have gotten a lot more pale. I'm going to heat this just a little more just to ensure that I've driven off all of the water. Okay, so upon heating the hydrated solid more, notice that the crystals have gotten a lot more pale. Notice also that the crystal size is smaller than before. I did that because I wanted to increase the surface area of contact with the solid and the evaporating dish. And note also that I spread it out more over the evaporating dish. That is to give the crystals more contact with the evaporating dish so that evaporation occurs more completely. Okay, upon heating the sample again, the mass is now 56.69, and that was exactly what it was before. So I'm going to assume that I've driven off most, if not all, of the water. Just to show that you can rehydrate the sample, I'm going to add water back to it. I just want you to see notice what occurs. And predictably, the solid returns to its original blue color. Notice the smoke that's appearing there, and that's because this reaction is giving off a significant amount of heat.